In this electrolytic cell, we have a solution of copper 2 sulfate, and we are running a current of 2.25 amps. And remember, amps is coulombs per second. And we're trying to deposit 1 gram of copper solid at the cathode. And they're asking me to solve for the minutes, how long we're going to need to run this cell. So it always starts though with writing out a balance equation for what is being produced here. So we know that we are starting with a solution of copper 2 sulfate solution. So inside of that is really copper 2 plus ions, and it is being reduced by gaining 2 electrons into copper solid metal, and that's being deposited at the cathode. So what we are trying to produce is 1 gram of that, and I need to know, well, pretty much how many electrons do we need to do that? So we're going to start here with 1 gram of copper, and first step, always convert that over to moles using molar mass, 63.55 grams of copper for every 1 mole. Grams of copper cancel out. Now, looking at your balance equation, you can see here that for every 1 mole of copper solid that is produced, we require 2 moles of electrons. So that's our next step, is a little bit of stoich. 2 moles of electron for every 1 mole of copper. Moles of copper cancel out. And now, to convert this over to charge, this is where you're going to use F, Faraday's constant. 1 mole of electron has a charge of 96,485 coulombs. Now, you don't need to remember Faraday's constant. That's always going to be on your equation sheet. So now I'm going to calculate the coulombs needed for this reaction, and we get 3,036.5 coulombs of charge that are needed. And now I'm going to calculate the amount of time. Looking at your equation sheet, you can see that this equation of I is equal to Q over T. I is your current in amps, and Q is the charge, and T is time in seconds. So I is really amps. How much charge for every second? That's your current, and it just happens to be measured in amps. So I'm going to use that to calculate time, because we just figured out charge. That's the amount of coulombs needed for this reaction, that 3,036 coulombs that we want. So we're going to go back and calculate the amount of time in seconds. All right, so this amount of coulombs is Q in that equation of I equals Q over T. Coulombs is charge. And what I am told in this problem is that 2.25 amps is our current. So 2.25, I'll plug that in for I. So this is really I up here. And so 2.25 coulombs per second is a unit of amps. I plug in the Q of 3,036.5 coulombs. And what I'm solving for down here is T, okay, time. And so time is going to be equal to 1349.56 seconds. Okay, current is measured in coulombs per second. Now I need to convert this over to minutes. So I know I'm going to have to divide this by 60, and so the seconds can cancel out, and we are left with 22.5 minutes of how long we're going to have to run this cell. Okay, so we calculated coulombs, then we plugged the coulombs into the current equation, meaning amps, and we solve for T. Now I'm going to show you an alternative way to do this, all just in dimensional analysis. All right, so the alternative way to do this, all dimensional analysis, is to do everything the same way. You go from your grams to your moles of copper to your moles of electrons and then to coulombs. And then after this step, we can use the current in amps as a conversion factor. And we know that the current was 2.25 amps, and really just saying that capital A 2.25A is really saying 2.25 coulombs over 1 second. That's what it's saying. And so I'm going to use that in dimensional analysis. And so 1 second is equal to 2.25 coulombs. So that coulombs cancel out. And then now I can convert this over to minutes. 1 minute is equal to 60 seconds. 60 seconds on the bottom, seconds cancel out, and you are left with the unit of minutes. And that's going to give you the same answer of 22.5 minutes.